Oh, wow, it's a wonderful moment to be here once again. Today, we want to consider electrolysis, but then I want you to do two things for me. Kindly subscribe if you are new in this channel, and the number two thing is that please forward these videos to your friends that you know that they will be in need of these notes because you are going to gain values from this class today. Okay, have you subscribed? Wow, thank you. And if you have any question, you can just drop in the comment section. Be very sure that I'm going to attend to them. Now let's start the class proper. You are going to enjoy it, trust me. Now I want to introduce electrolysis. Now let me introduce electrolysis by saying that if an electric current is to pass between 2 points, two different points, there must be a movement of charged particles. Even by the definition of what electric current is the movement of ions, is the movement of electrons. Rather, it is the movement of electrons, and definitely before that electron moves, it must be between two different poles. And the two different poles that we have in chemistry are the cathode, which is the positive, and then the anode, which is the negative. Now, the positive cathode, that's for the electric current, and the negative anode is also for the electric current. So that is, there must be that ions that are free to move. All right, in this class, what are those things you should expect? In this class today, we are going to be describing some terms that are used in electrolysis. I'm going to introduce electrolytic cell to you, factors affecting preferential discharge of ions. Then we move to calculation proper. Is somebody excited to be in class? All right, let's move. What is electrolysis? Electrolysis is a process whereby chemical decomposition occurs. Know that word, chemical decomposition. Chemical decomposition occurs when an electric current is passed into an electrolyte or through an electrolyte. So that electrolyte is the chemical that is decomposed. If you look at the diagram, in the note, you will see something that looks like a bucket, and then you will see two different charges in the bucket. Now that different charges you are observing there is the chemical, and that chemical is regarded as electrolyte. Then we have the battery. The battery that is there is the one that fast track or that aided the decomposition of that chemical that we call electrolyte. All right, let's move. Let us also consider some other terms that are used in describing electrolysis. We have electrodes. What are electrodes? Electrodes are conductors in form of wires. In this case, the electrodes that we are talking about, they are not in liquid form, they are in solid form. Electrodes are in form of wires, in form of rod, in form of plate, through which electric current enters or leaves the electrolyte. So they are just terminals. They are terminals through which electric current enters into the electrolyte or leaves the electrolyte. And majorly, we have two types of electrodes. We have two types of electrodes, or two terminals of the electrodes. We have the cathode terminals, and then we have the anode terminals. When I was introducing the class, I told us that for the electricity, the cathode is the positive terminal, whereby the anode is the negative terminal. But in electrolytic cell, they just interchanges. The cathode that is positive for electricity is now the negative. So the anode is the cathode is negative for the electrolytic cell, whereby the anode is what is positive. I said the cathode is what is negative for the electrolytic cell, whereby the anode is positive for the electrolytic cell. Just an exchange of what of ions. Now let's move to the second one, electrolyte. What is electrolyte? An electrolyte is a chemical compound like the one I showed in the previous slide. Is a chemical compound in a molten or aqueous state. Note that word, molten means without water. Aqueous state means with water. That means that compound, that electrolyte, you've dissolved it inside water, or there is a water inside the chemical, which or aqueous state which can conduct electric current and is decomposed in the process. So electrolytes are also conductor, but in this case now they conduct by ions. They conduct in form of solution. They are not in solid. In electrolyte in solid state cannot conduct electric current. It's only when they are in liquid, when they are in aqueous, or when they are in molten form that they can conduct electric current. Molten form means that chemical is without water. Maybe that chemical is melted. That electrolyte is melted. Now, electrolytic cell. Electrolytic cell. Before I describe electrolytic cell, you need to see this diagram again. Now, this diagram that you are seeing here is a typical example of electrolytic cell, because it's just the assembly of electrodes. Those two rods that enters into that thing that look like a bucket are refers to as electrodes. So when we talk about electrolytic cell, it is an assembly of electrodes in an electrolyte, and it is used for what? For electrolysis of substance. It is used for electrolysis of what? Of a substance. Let's quickly move. Now this is a simple electrolytic cell. This is a simple electrolytic cell. The labeling part up there, you have the DC current. That DC current is the direct current, or you can call it battery. It is that electricity that enters into the electrolytic cell. Like I explained earlier, the cathode of the electrolytic cell is negative, whereby the anode of the electrolytic cell is what? Is positive. Okay, so in that, the cathode is the negative electrode and the anode is the positive electrode. So electric current enters into the electrolyte through the cathodic terminal, because it is the negative electrode. Do you get it now? Because electron moves via the negative pole. So those ions inside the electrolytic cell, mainly the electric currents enter, they dissociate, because an electrolyte is made up of two ions, the cations and the anions. So mainly electric currents enters into the electrolyte, the ions split and migrate to their respective poles. So for the cathode, since cathode is negative, cathode attracts cations, positive ions, and since anode of the electrolytic cell is what? Is positive, it attracts anions. So in my terms, I said cathode cations. That is, the cathode of the electrolytic cell attracts cations, and I said anode anions. The anode of the electrolytic cell attracts anions. Are we following? So let's quickly fast track principles of electrolysis. Which principle does electrolysis operate? Now read with me. An electrolyte composed of positive and negative ions. Every electrolyte is made up of ions. The positive, which are cations, and the negative ions, which are anions, during electrolysis. So electrons move from the negative pole of the battery. So the negative pole of the battery is the anode, and the negative pole of the electrolytic cell is the cathode. So to the anode, to the cathode. So to the cathode of what? Of the electrolyte, making it to be electron rich and negatively charged. Okay, so the electrode, the cathode of the electrolytic cell is what? Is negatively charged. Hence, positive ions migrate. So like I've explained earlier, that the cathode attract the cations and the anode attract the anions, and that is the summary of the principle of electrolytic cell. All right, let's move to factors affecting preferential discharge of ions. Number 1 is the position of ions in the electrochemical series. Number 2 is the concentration of ions in the electrolyte. And number 3 is the nature of the electrode. Now we are going to consider this one after the other. How does the position of ions in the reactivity series, now reactivity series is the same thing as electrochemical series, affect discharge of ions in the electrochemicals? How does it affect? Now when we say preferential discharge of ions can also mean selective discharge of ions, whereby we have two ions and the one is invariably discharged over the other, and there are factors that affect it. So the factors that affect which one is being selectively discharged are the one we are discussing right now. Which one is discharged in preferential to the other. Now, how does the position of ions in the electrochemical series affect which ion will be discharged? Number 1, the way ions are arranged in the electrochemical series, they are arranged in decreasing order of their reactivity, of how powerful they are. In decreasing order. So those cations like potassium, sodium, calcium, they are highly electropositive, and that's why they are up. So mercury, starting from hydrogen ion, copper ion, mercury, silver, gold, copper, those ones are less electropositive. Every ions above hydrogen are more electropositive than hydrogen, whereby every ions below hydrogen are less electropositive than hydrogen. Do you understand now? So which means that the one that are less electropositive will be discharged in preferential to the one that are highly electropositive, because the one that are less electropositive has lesser energy to be discharged when compared to the one above in the electrochemical series. So in summary, for cations, the ions that are positively charged, every ions above hydrogen will never discharge whenever they are together, whenever they are competing with hydrogen. Take for instance, if sodium is competing with hydrogen now, sodium will never discharge because it's highly electropositive than hydrogen. So hydrogen will be discharged in preferential to sodium. Why? Because hydrogen is less electropositive when compared to sodium. Now the same vein, if hydrogen and copper are in the same solution competing for which one will be discharged, copper will be preferentially discharged to hydrogen. Why? Because copper is less electropositive to what? To hydrogen. So in summary, ions that are less electropositive will be preferentially discharged to the one that are highly electropositive. The same thing goes for anions. OH minor, which is hydroxide ion, is mostly preferential discharge to others in the series. Why? Because it is less electronegative when compared to others. Alright, concentration. Now, concentration will only affect ions that are relatively close in the activity series. Ions that are relatively close. Take for instance, when we are doing electrolysis of sodium chloride, dilute sodium chloride and concentrated sodium chloride. For dilute sodium chloride, it is hydrogen that will be discharged at the cathode, and then at the anode it will be hydroxide ion. But when we are talking about concentrated, because of the distance between hydroxide ions and chloride ions are not too far, they are relatively close. Because of the increase in concentration, instead of hydroxide ion being discharged at the anode, it is chloride ion, which is Cl minus, that will be discharged at the anode. And that is how concentration can actually have effect It will only have effect with ions that are relatively close in the activities series. Now, nature of the electrode. This nature of the electrode will only have effect if, because when we talk about nature of electrodes, we have inert electrodes and active electrodes. Inert electrodes are electrodes that does not take part in the electrolytic process, like graphite and carbon. Are you with me now? Like platinum and carbon. Carbon can also mean graphite. All right. Those two are called inert electrodes because they do not partake in the process. They don't partake most of the time in the electrolytic process. But electrodes that have interest or that have affinity in the ions of the electrolyte, when you use such an electrode, it will affect the ions that will be discharged. Like electrolysis of copper 2 sulfate, and then you are using copper as the electrode. Definitely, the expected ions will not be discharged just because copper is also there. So electrodes that are active can affect the ions that will discharge at the respective poles. Like when we use mercury as electrodes, mercury can affect the ions that will be discharged when we are doing electrolysis of sodium chloride. All right, so let's fast track. Up next is Faraday's law of electrolysis and then calculation involved. Faraday's laws of electrolysis and calculations involved. Okay. Now, Faraday's first law, we'll be dealing with Faraday's first law and then the calculation involved. Faraday's first law states that the mass M of a substance liberated or deposited at electrode during electrolysis is directly proportional to the quantity Q of electricity passing through the electrolyte. What Faraday is trying to explain here is that the quality of electric current that pass through the electrolyte determines the mass that will be deposited or the gas that will be evolved. So in that case, Faraday law is trying to explain to us that the quality of the product we can get during electrolysis is depends on two factors. Number one is depends on the magnitude of the current, and number two, the time flow of the current. And that's why we now have Q is directly proportional to the mass deposited. How powerful the current is determines the quality of the product you are going to get, and Q is a product of current and time. Now, let's see some derived formulas for calculating electrolysis. Derived formulas for calculating questions involving electrolysis. 1. We have Q multiplied by F. That Q multiplied by F is equal to molar mass divided by mass deposited, then Q multiplied by F divided by capital Q, and that capital Q is a function of current times time. All right, now let me quickly explain that. When we talk about Q, that Q is the charge on the ions. The charge on the ions. Like for cations now, the charge on them is the Q. Take for instance, aluminium. The charge on aluminium is 3 plus. So because the charge on aluminium is 3 plus, so anytime you want to apply this formula, that Q is now 3 multiplied by the number of Faraday. Now Faraday is just constant. It's a constant figure, which is 96,500 coulombs. Then the molar mass is different as the atomic mass of the element. The atomic mass of the element over mass deposited. Note that molar mass will be always greater than mass deposited. Mass deposited is just a fraction. It's just the mass, the value is not as large, or is not as big as molar mass. All right. So this formula is strictly applicable when we are dealing with metals deposited at the cathode. Most of the time you can easily make use of this formula when you are dealing with metals deposited at what? At the cathode. Now when we are now dealing with gas, we can make use of this one. Instead of talking about molar mass, we change it to molar volume, and instead of talking about mass deposited, then we make use of volume deposited. So molar volume is a constant value, and the value is 22.4 dm cube. And note that the volume deposited must also be in decimeter cube. So if the volume is not in decimeter cube, we might need to do a conversion from what? From centimeter to decimeter, and that means that whatever value that is in centimeter cube divided by 1000 in order to convert that value to what? To decimeter cube. So this formula can be used when we are dealing with gaseous substance, and most of the time when we are talking about gas are being liberated at what? At the anode. Now let's see some practice question. Let's do some practice question. Applications of this formula. Calculate the quantity of electric current in coulombs required to liberate 10 grams of copper from a copper compound. Now look at how we are going to solve it step by step. Step 1, we are going to write the ionic equation. Actually, when you are solving this in theory, it is important that you write this ionic equation. You know, the charge on copper is what? Is 2 plus. The charge on copper is 2 plus, and then we have 2 electrons in order to balance the number of charge. The number of mole of copper at the reactant side, at the left hand side, is 1, and the number of moles of copper at the product side is also 1. But what left now is that we use that electrons to balance the charge. Copper is 2 plus, so we have 2 electrons in order to balance the charge, so that plus 2 minus 2, the total charge on the reactant side will be 0. Any free element, the total charge on any free element is also 0, and that's why that ionic equation there is balanced. I always advise my students that whenever you are dealing with questions like this, you itemize what you are given in the question so as to know how to apply the formula. So in this case now, the charge on copper is 2. The molar mass of copper, which is the same thing as the atomic mass of copper, is 64. The Faraday, is constant. Faraday is 96,500, and then the mass deposited is 10 grams according to the question. So if you remember the formula I gave, that means that what we are left with now is our Q. If you check this one now, you see that this Q is what is missing now. So we are going to make Q the subject of the formula. And by the time we substitute everything into the formula as I have highlighted it. If you are solving this type of question in theory, make sure you follow the due process so that you will get full mark. So if you substitute every value into the formula, our Q will eventually be 30,156 coulombs. Let's look at another question. Calculate the volume in centimeter cube. Note that now, in centimeter cube of oxygen. Calculate the volume in centimeter cube of oxygen evolved, or definitely it's oxygen gas, evolved at STP when a current of 5 ampere is passed through acidified water for what? For 193 seconds. Note that our times is always in seconds. So whenever we are given time in minutes or in hours, we are going to convert it to what? To seconds. And what's the unit of conversion? If your time is in hours, you firstly multiply by 60. Let's say it is 1 hour. You multiply 1 by 60, that will be 60 minutes now. So that 60 minutes multiplied by another 60 to convert it to seconds. Let's say you are given 1.5 hours. That means that 1 hour 30 minutes. If I were you, I would just convert everything to minutes first. So 1 hour is 60 minutes, and then another 30 minutes, so making 90 minutes. So that 90 minutes multiplied by 60 in order to convert it to seconds. But this one is already in seconds, so we don't need any unit conversion. So just like we did in the previous slide, substitute those values into the formula. In this case now, the number of charge here is 4 minus. That minus is none of our business, is the charge, which is 4. That is our concern, because we are adding 4 electrons there. So the 4 here multiplied by the 4 beside hydroxide ion multiplied by the charge, which is -1, make it -4. So the charge there is 4. The number of Faradays is 6,500. Now in this case, we are not going to be using molar mass of oxygen gas. Rather, we'll be using molar volume, because it is a gas. We don't regard the molar mass of the gas at STP. In this case now, we'll be applying the molar volume, which is 22.4 dm cube. And then our Q can be easily calculated because it is current times time. And our time there is 193 seconds multiplied by 5 to give us our Q. Then we make our volume liberated the subject of the formula. Now if you substitute the value into the formula, our volume will be 0.056 dm cube. So because it is in dm cube, we are going to convert it to centimeter cube. So if you are converting from dm cube to centimeter cube, we multiply by 1000. From dm cube to centimeter cube, we multiply by 1000. But from centimeter cube to dm cube, we divide by what? By 1000. So I want you to do this on your own. These 3 questions, you can just drop your answer in the comment section. So if you have not subscribed, kindly do well to subscribe. Thank you for coming to the class. Just go through the notes again, and if you have any question troubling, you just drop in the comment section. I just want you to know that you can be an emblem of success without compromise. So till I come your way next time, shalom.